All right, are we ready for page 16? There we go. Okay, so last time we got this one started, we have a horizontal box, a horizontal surface, and we put a box on it, and we have to give it that initial quick push. Did I demonstrate quick push versus constant push? Maybe with my podium here. And so quick push is just to get it in motion. But really the focus of this problem is that slowing to a stop. And so that's what we drew the force diagram for. It was during the stopping, okay? And so they gave us the initial velocity. Stopping would be the final velocity. They gave us a distance and then said, find this coefficient of sliding friction. And so it looks like we got our diagram and we all get that there's no applied force, yes? A lot of students want to put an applied force just if it's moving. It was pushed in the past, but it's not being pushed in the present. Okay, and so step 2, FNet statement. FNet, I'm going to start with the horizontal motion here because it's moving in the horizontal. Technically, there's 2 statements. We'll get to the other one here in a little bit. And so Newton's second law, FNet equals MA, and we only have one force in the horizontal. And it looks like we defined the right as the positive direction. And that's not because it's right. For me, forward is positive. That's what usually works for me all the time. And so forward is positive. They said it was moving to the right. So friction is a negative force. Everybody good with what we did last time? All right. Now we need to plug in our new equation for force of friction. And so now I'm going to keep that right side going. MA, okay. That one we'll deal with in just a second. But force of friction, who remembers our new equation? New equation. It's either on page 14 and/or it's on our formula chart, mostly. Yes. Yes, it's the coefficient of friction. It's that Greek symbol mu. You can just say coefficient of friction. And kinetic, because they told us they want us to solve for the coefficient of sliding, AKA kinetic friction. Plus we're looking at the portion where it's in motion. And so remember, kinetic is motion, moving. Okay, so mu K times Fn. Now I'm just putting it in parentheses because that negative is the negative force. I don't want you thinking it's a negative coefficient. There is no such thing as a negative coefficient. Well, let's keep it going. Tell me more about the normal force. On our diagram, it looks like we already said it. On this one, normal force is also equal to the gravitational force. We had one down force, gravitational. We have one up force, normal, and there is no applied force. No, there's no other vertical pieces to it. And so we can plug in for Fn, Fg. But wait, there's more. What can I plug in for Fg? What is a gravitational force? Say again. Not just 10. I'm assuming that 10, you're saying gravity, right? 9.810? Yeah. But there's more to weight than just the acceleration due to gravity. mg, okay? And so it's the gravitational effect on our mass. That's where I use the thought experiment. What if we go to the moon? We change our weight, but we don't change our mass, okay? And so now I'm just going to bring everybody else down. And so now we're at this point. And again, what we're trying to solve for here is that coefficient of sliding or kinetic friction, okay? And so G, we know. What about mass? Did they give us the mass on this problem? Did they tell us what the mass was? Oh no, they didn't give me the mass. I guess I can't do the problem. Worthless, right? Impossible. That's what students say. Watchy watch. You ready for this? I don't think it's our first time, but just in case it is, I promise it won't be the last time. What I'm about to show you is very common in forces. It's also common in energy, circular motion, momentum. It's very, very common, okay? And so if we look at where we left off, if we're trying to solve for the coefficient, what do we got to do with mg? Before you plug in numbers, what could you do with mg? To isolate the coefficient. Yes. Divide, and I'm going to go and divide out that negative. And notice it cancels on the right. And what happens to mass on the left-hand side? Whatever it is, it cancels on the other side. And so what that means is, conceptually, this is independent of the mass, okay? Mass on the left, mass on the right, as long as it's all the same mass, it'll cancel out. It happens so often. Y'all remember the tie-dye teacher that I showed you the video of last time? He did the friction experiment. Okay, Mr. Palmer is his name. It's so common in physics, he wrote a theme song about it. So if you want to, watch that video, his phrase is, everybody brought mass. Everybody brought mass. Anyway, mass cancels. Good deal? And so if you read a problem and they don't give you mass and you think, oh, I need mass, hold on to the M. Keep it in variable form as long as you can. Mass should cancel out. Okay, so now what's left? We have mu k equals a negative ax over g. Whether the negative is on the left upper or lower portion, it doesn't matter. And so we know g. Do we know the acceleration? Was it given? Is it 10? They didn't give it to us, but they gave us some kinematic terms, right? So initial velocity is 10, then final velocity is 0. And we know it happens over a distance of 20. Now don't do anything crazy like, oh, 20 over 10 is 2. Or 10 over 20 is 0.5. Use a kinematics equation, right? And so let's use kinematics. Initial velocity at the beginning of the slowdown, 10 meters per second. Final velocity during the slowdown, 0. And it takes a distance of 20 meters. And we want to use this to find our horizontal acceleration. So what kinematic equation are we going to use? Third one. And so VF squared equals VI squared plus 2A delta X. So 0 squared. Y'all know the drill here, right? 10 squared is 100. And then we got to subtract it to the other side and divide by the product of 2 times 20. So yes, we will get a negative answer, and that's okay, right? We're moving forward, but we're slowing down. And so what's 100 over 40 or 10 over 4? 2.5. And so now we know the acceleration. Now we can divide by gravity and get our coefficient. So a negative 2.5, what's going to happen to our negative? It goes away, it cancels out, reduces to positive, and 2.5 divided by 10, 0.25, which if you remember last time, I said that 99% of our coefficients are going to be less than 1. And this is less than 1, so that makes sense. Before I leave it, what's our SI unit for the coefficient of friction? You're shaking your head no, why? Doesn't have a unit, because if you go back to the original equation, frictional force divided by normal force, Newton over Newton, leaves you with nothing. And so that is your complete final answer. And just in case future problems, you end up with 10 or 12 digits, most coefficients are to the hundredths place, okay? If it makes you feel better to put a third, okay. But don't give all 10 digits. Questions? Yes. Say again. Most coefficients are in decimal form. I'm just letting you know. But yeah, fraction, what was it? 2.5 over 10. I mean, technically it's still equal, but they won't give you coefficients in fraction form. And if you pull up that Wikipedia list I talked about, they're all in decimal form. Okay. Part 2 of this same problem. Now, what if we fill the box with rocks, increasing its mass, and you again start it moving at, we need to make a correction here, okay? Accidentally grabbed the wrong number. Instead of 20 meters per second, it should be 10 meters per second. Good scientist only makes one change at a time, yes? We can't fill it with rocks and start it at a greater speed. And so now, same initial velocity. So we might have to push it a little harder in the beginning to get it moving. But this is all about the slowdown. When you fill it with rocks, how far does it travel as it slows down? Any thoughts? So we've got the same initial velocity. We've got the same final velocity. We're trying to figure out this displacement. And if you're like, those are kinematic terms. Yes, they are. We need to decide, well, does it have the same or a different acceleration? And so to figure that out, maybe we start with forces. It's still a box sliding across a floor, slowing down due to friction, right? The only difference is it's more massive. And so we still have an F net equal to that frictional force in the negative direction. The acceleration is going to be in Newton's second law. F net equals ma. Everybody say that with me. F net equals, F net equals, and F net equals. Okay, so much gusto there, right? And I only do that because I'm students that are coming in or whatever, they say F net equals FA. They put in an applied force and they don't ever break it down to mass times acceleration. Okay, F net equals, okay. So it also equals that frictional force when you sum the forces. And so we can still plug in that mu, I'm gonna go straight for it, mg. So let's use forces to find the acceleration. By the way, did they tell you how many rocks they put in the box? They did not. Does it matter? What's still gonna happen? Even if you fill the box with rocks, MR, what's gonna happen? Gravity's the same. Did they mention changing the surface? If you remember, we talked about the coefficient of friction is surface dependent. Okay, there was no mention of that. And so if the coefficient is the same and gravity is the same, Acceleration's the same. Hint, hint. How far is it going to slide until it stops? And everybody says, same. So you could either say same or whatever the original distance was, 20 meters. So it's independent of the mass. Now, again, if you're like, but you told us that heavier objects, you got to push them with more force. That's to get it moving. But this problem is talking about it coming to a stop. I'm no longer touching it. So maybe in the beginning, you have to push it harder to get the same initial velocity. But when it slows down, mass cancels. It's going to be the same. Good deal? Okay. We're not done with the coefficient of friction. In fact, that one only had kinetic. The problem that we'll do here in a little bit is going to be this one down below. I'm going to do a different one first, but it has friction, and they actually give you both the static and kinetic coefficients. And if you remember, static is always greater than kinetic, and that's true here. And so before we do this one, let's go back to page 15. How about we do a frictionless ramp first, right? Now, on the AP exam, maybe half your surfaces have friction, half don't. But when you see a frictionless ramp or a frictionless surface, inside, do the little happy dance, right? It's one less thing to worry about. And by the way, is that real life? A frictionless surface? No, we can only come as close to it if what kind of surface we have. Ice, right? Even maybe wet ice, slippery ice, right? Or if, you know, a can of oil spills on the floor, that's pretty slippery, okay? Not much grip. Now, before we do this problem, maybe we introduce this idea of ramps. So I'm sliding over to the right. We're going to do some ramp lesson first. And so this is not a ramp, right? This is a box on a flat surface. What does it take to make this surface a ramp? You tilt it one end, right? And so this becomes maybe something like this. We tilt the surface, the object that's on it tilts as well. And so our old XY axis, so old X and old Y, old Y are what we're used to. But now, with our tilted surface, and what I'm about to say, you can choose or not do it, but if you tilt your head, like the ramp, then where's our new X? New X is also parallel to the surface. Okay, two parallel lines. It's parallel to the surface. Now, I say that because some people like to just say new X, old X, X is X, right? Personally, ramps are such a special case, and I want you to know that it's a special case. I'm going to be using the subscripts parallel, okay? But feel free to use X if you want. Well, when you tilt the X-axis, what has to happen to the Y-axis? X and Y, by definition, have to be 90 degrees from each other, right? And so if X tilts, so does Y. Watch my arms for a second. Old XY, if you tilt the X, Y has to tilt as well. And so now we get new Y, or what I like to call the perpendicular. It's perpendicular to the new surface. Everybody good? Well, what if we put these two axes together? And so I'm going to take that old XY, old X, old Y, and we do a little geometry. Now my picture is getting a little cluttered here, but old X and Y are the black dashed lines. New XY are the red lines, dashed lines. Well, if we think about theta, the angle they gave us, isn't theta separating old horizontal and new horizontal? Theta, my surface, got tilted, theta. Well, take it to the dashed lines. Isn't that same theta right here? Old X to new X. And so theta, oh, that looks yucky, but it should be there. Don't worry, we'll draw a clean, simplified one here in a second. But if that's theta, isn't old Y to new Y also theta? And then keep it going to the other side of the old X-axis to the new X-axis. That's theta. And then for the old vertical down below and the new vertical, here's your theta. Does everybody get that when your surface tilts, your whole axis tilts by the same amount? Okay. So again, that got a little cluttered. Let me draw fresh. Actually, let's draw the new one with a force diagram. Now we do need to kind of give us some kind of story to it. So I've got a box on the ramp. Let's just say it starts from rest. We did one of these early on with our force diagrams. But let's do the same box on a ramp. At rest, is every problem at rest? No. So what forces are acting on this object at rest? We got gravity. Now from center of mass, make it kind of big. Okay, just because I'm gonna use it, we're gonna work it. And I would recommend putting your label not on the left or right side, you'll see why. Put it at the bottom of the arrow. What other forces are acting on this box at rest? Normal force. By definition, we draw normal force, what direction? Perpendicular to the surface. Our surface is now tilted. Our perpendicular axis is tilted, right? So don't go straight up, go up and a little to the right? Now trust me, draw it smaller. Fn should be less than Fg. I gave a little clue to it last time. I'll show you another way it's smaller today. Now, if this alone are the forces acting on it, it would not be at rest. What's the only way for this box to be at rest? There's got to be some kind of grip holding on to it, right? Gripping friction, AKA static friction, okay? Now, it wants to go what direction? What's the would-be motion? It wants to go down the ramp, so friction has to grip up the ramp, parallel to the surface. Don't draw it super big either. We've already learned that frictional force is typically less than the normal force because of that coefficient. Any other forces acting on this object at rest? There's no strings, no fingers holding it in place. This is it. Now, if you look at it with the typical old XY axis, you would have two vectors at an angle. But why do two vectors at an angle when you could just tilt your head and have one? And so here's where I'm going to draw those new axes, kind of in line with our force diagram. Fn is on the perpendicular axis, or new y, if you prefer. Ff is on the parallel axis, or new x, if you prefer. And so if those two forces line up with the new axis, what if we just say gravity is the vector at an angle? And I didn't ask it earlier, but does gravity care if your surface is tilted? No, gravity's trying to pull you to the center of the earth always. Question? Yes. And so gravity becomes the vector with components. And again, it's going to dirty up a little bit, or we're going to add to it. Let's draw in the components for gravity. Gravity, 9.8 that we know, right? If this was 1 kilogram, 9.8 is not the acceleration of an object sliding down a ramp. It's for an object in free fall, right? So some of this gravity is actually going to be supported by the ramp, and some's going to allow it to come down the ramp. So here's the way I do it. Fg perpendicular, or FGY if you prefer, is opposite Fn. Opposite because 99.9% of the time, those two are going to balance out. And so your FGY, or Fg perpendicular, is equal to Fn. And so we can say Fn is equal to Fg perpendicular. Then maybe you start to see a triangle forming with Fg. I need the parallel component. Parallel to what? Parallel to the surface. Now, some textbooks and some videos, they'll actually put it along the parallel axis. Fg parallel. Okay. And this is fine, but I don't really see a right triangle, but parallelogram, true story. Can I pick Fg parallel and do tip to tail with Fg perpendicular and it be right here? Isn't that the same thing? And notice your parallel and perpendicular component are 90 degrees from each other, as it should be. X and Y should be 90 degrees from each other, yes? And if you draw it this way, which you should, notice Fg, the actual force, is what part of a right triangle? It's the hypotenuse. And I'm going to highlight that because a lot of students start drawing their own type of triangles where Fg is the vertical component or the X component. They're doing the triangle wrong. And so again, how I draw the triangle, I got my Fg. I draw Fg perpendicular, opposite Fn. And then I do my best to draw the parallel component parallel to the surface, 90 degrees from the perpendicular component. But Fg will always be your hypotenuse. Okay. Now, for us to get an expression for this, how to solve for normal force, how to solve for Fg perpendicular, I need to know where that ramp angle is. And so maybe in the problem, they give you theta on the actual physical ramp. That theta is somewhere in my gravitational force triangle, but where? So go back to the geometry we started with. Old xy, when the x-axis tilts theta, how much does the y-axis tilt? Theta as well, right? Same angle. Well, gravity, Fg, is on the old y. Fg perpendicular is on the new y. And so that shift between FG and FG perpendicular is the same angle as the ramp angle, okay? And if you want to go back and look up above at what we did here, it's this angle that we're identifying, okay? That's the same angle. Do you love ramps yet? No. What happened to the good old days when your surface was flat? But anyway, okay, so now using just that gravitational triangle, let's write out an expression for FG perpendicular. And so FG perpendicular, notice with my angle identified, it's adjacent. And remember, FG, the actual weight of the object, is the hypotenuse. And so what trig function will we use to find the perpendicular component? Cosine. And so it's going to equal FG, hypotenuse, times cosine theta. And that's your ramp angle. We can actually go one more step. How do you find the weight of an object? We said it earlier. The weight of an object, FG equals mg. And so FG perpendicular is also equal to mg cosine theta. And y'all, I'm going to highlight that one. It is used so often, okay? Maybe they ask you for the normal force. Maybe you need the normal force to find the coefficient of friction. And most times, 99% of the time, the angle given is where it's identified here. It's the ramp angle with the horizontal. And so the trig works out to be this 99% of the time. If you like to memorize and want to memorize this, you so can. But just know, you can also figure it out from a force diagram drawing in your components. What about FG parallel? And I'm going to use the one that's part of the triangle, okay? So FG parallel is opposite theta. And again, FG, the actual weight of the object, is your hypotenuse. What trig function will we use to find the parallel component? Sine. And then last step, FG equals mg. And so FG parallel, or x if you prefer, is mg sine theta. Now for students that are used to angles being only along the horizontal, you're like, that's backwards. But again, go back to that above geometry. It's still the angle with the horizontal, but gravity is a vertical force and it had a shift. The perpendicular new axis is shifted theta. And so draw your triangle out. This is correct. Questions? Okay. So with those in mind, let's go solve a problem. And so on page 15, this same page, we've got a box. Now it's a frictionless ramp, so we're not going to draw friction. It's held at rest, so we're still at rest by a tension force. The mass of the box is 20 kilograms. Now they're telling us, but just be ready, you're not always told, draw a free body diagram for the block. And so what forces are acting on the block? We got gravity. It's our big force down. And we've got normal force, tilted, right? Perpendicular to the surface. So it's that northeast, smaller than gravity. And then there's that tension force. And from the picture, tension is pulled parallel. So it's going to be what direction? up the ramp. And notice the string is parallel to the surface. So that's not the rule. It's pulled with the rope, but here it would still be parallel to the surface. It's frictionless. No fingers or no pushing or pulling here, so this is it. Now, if this was the AP exam in May, this is what you would give them for a final force diagram, okay? They don't want components on your diagram so much, they actually put that in the instructions. Draw all the forces, label the forces acting on the object, parentheses, do not draw components, okay? I don't really know why they took that or they added that part in. My guess is from, looking at student papers, are you noticing I'm drawing the components with dashed lines? A lot of students draw it with solid lines. And so that indicates to the person looking at it, it's a second and a third gravitational force, which is incorrect. And so I don't know, maybe that's why. Maybe they just prefer a cleaner diagram, but this would be the diagram you give them. But I'll be honest, if you leave it here, a lot of you are going to forget about FG parallel and FG perpendicular. So I say, draw one on the side, your chicken scratch diagram. Let's draw the components. And so watch my procedure. I'm going to start. Ooh, what happened? Hold on. I'm going to start by drawing an equal and opposite force, Fn. And who is it? It's FG perpendicular, or FGY. And then FG parallel may or may not be equal to your frictional force, or tension force, sorry, but it should be perpendicular to that FG perpendicular, FG parallel. And make sure you draw it this way so that FG is your hypotenuse. And the last thing to label, where is theta? Old Y to new Y. It's right there at the top. And if you start with going away from Fn, your angle's always going to be there. Good deal? Okay. What is the value of the tension force? So tension varies just like friction does based on whatever it needs. And so here tension is in the parallel direction. And so maybe we start by writing an F net parallel or F net X. And notice how many parallel forces do we have? We got tension. Don't forget about FG parallel component, okay? That's the one that people are going to forget. And so I have not decided what direction is positive or negative. So what do y'all want? Up the ramp or down the ramp is positive? Up. So if up the ramp is positive, I'll say FT is in the positive direction, minus, because gravity pulls you down the ramp, FG parallel. F net equals what? MA. And this is a parallel acceleration, right? You're accelerating, if any, parallel to the surface. Well, on this one, are we accelerating? It said it's held at rest. So what's the acceleration of an object at rest? 0. And so really what that tells us, if you add FG parallel to the other side, the down the ramp and up the ramp forces are equal. And so to find tension, just solve for FG parallel. And not that I expect you to memorize 5 minutes ago, but if you look at the triangle, which trig function is the parallel component going to use? Sine or cosine? Sine. FG parallel is opposite theta in my triangle. And so it's that mg sine theta. So I plug that in for my FG parallel. They said the mass is 20 kilograms. G, we can use 10. Sine times 30. And so hopefully you have a calculator. If not, go ahead and grab one. Or maybe you know sine 30 is 1/2, and half of 200 is 100. Newtons would be your tension. What if the angle was bigger? What would get concepts? What if theta increases? What's going to happen to FT? What if we keep it still at rest? Maybe I have a spring scale connected to that string, so it gives me a reading. Would tension be the same, less, or greater? Ooh, I hear both. Good. So let's go through this. Here's how you figure it out. Greater than 30. Someone give me an angle greater than 30. 60. Okay. So sine, I thought I heard 60. So sine 30, we just said, is 0.5. Someone do sine 60. Punch it out. What do we get? 0.8 something, 87 or 866, right? So as theta increases, what happens to sine theta? Sine theta increase, 0.5 to 0.87, right? What's going to happen to tension? It increases. So tension is going to increase when you increase the angle, okay? M and G would be the same. If all you change is the angle, tension would increase. Good deal? Okay. Next question. What is the acceleration after the rope is cut? AP loves to cut their ropes, by the way. So the first part of the problem, maybe the rope's there, and then the string is now cut. And so if you cut the string, goodbye, what force? Tension. And so now we would just have FG, and then that normal force, no tension. Now it says we're gonna accelerate, which should make sense, right? If it's frictionless, you don't have any string, you don't have any grip, who's there to keep it at rest? Nobody. So it's gonna accelerate down the ramp. And so F net parallel equals, now what force is bringing it down the ramp? Which force is bringing it down the ramp? Gravity, we say gravity, but it's a component of gravity. Make sure you think or draw these components. And so your parallel and perpendicular component, which one brings it down the ramp? Parallel. And so I'm going to say F net parallel. We sum the forces in the parallel direction. It's just FG parallel. And since we're moving now, I mean, I hate to contradict my prior statement, but is the box ever going to go up the ramp in this problem? Maybe earlier we could have pulled it up the ramp. Maybe we give it a quick push up the ramp, but none of that was presented. And so if you want to say down is positive, as long as you let your grader know that you're making a change, it's fine. And so if it goes down, then I can just say a positive FG perpendicular. It's going to go forward down the ramp. F net equals MA. Next time I ask, I want everybody to say it. FG parallel, we're going to use what function? Sine, same as before, but MG sine theta. And we're going to solve for acceleration. Now, y'all, even though they gave me the mass, I got mass on the left, mass on the right. Everybody brought mass. So what can we do? We can cancel it out. Okay, divide it out. Divide both sides by mass, cancels out on both sides. And so now the acceleration would be 10 sine 30. We already said earlier, sine 30 is 1/2. What's half of 10? 5 meters per second squared. Yes. Good deal here. Okay. And then a little callback. How long will it take? What are we solving for? How long will it take? Time. For the block to slide 5 meters, there's our distance, down the ramp after the rope is cut. And so originally, when you first cut the string, it starts from rest, right? 0. And we just found the acceleration is going to be 5 meters per second squared. How long will it take to travel 5 meters? Oh, we got to do what again? Kinematics. And so kinematics, callback. Again, the thing connecting kinematics and forces, acceleration. And so which equation are we going to use with acceleration, initial velocity, distance, and time? Second one. And so displacement equals VI t plus 1/2 AT squared. And it's not really horizontal, it's not really vertical. I mean, if you wanted to get technical, it's a parallel distance, a parallel initial velocity, and a parallel acceleration. Time is the only thing that doesn't care. Okay. And initial velocity, we said, is going to be 0. So 5 equals 1/2. A is 5, but be careful. Don't just say 5 over 5, 1. Square root of 1 is 1. That's wrong. It does reduce. We would get 1 equals 1/2 t squared. T squared would equal 2. Square root of 2 is 1 point. Punch it out. Square root 2. $1.4. Good. So a little callback to kinematics. Yes. Yes, I mean, that's fine. I'm just saying, like if you look at answers in the back of the book, if you look at AP rubrics, they always take it to the decimal number. But yeah, if you left it square root 2, that is equivalent. Okay, questions on ramps. That was the new piece. Can we do friction on a ramp? Can we do a ramp with friction? Let's try. And so back on page 16, let's do the bottom of that page. Okay. And so here, there's not really a story prompt. So let me tell you the story. We've got a box that maybe in the past, we hit it, we kicked it, we gave it a quick push so that it's moving 8 meters per second on a horizontal smooth surface. So if it's smooth and we didn't constantly push it, this is going to be a constant velocity here, right? And so this first part is a constant velocity. Everybody good on the flat surface? Now we did all that so that it'll have a chance going up the ramp. A stationary box can't go up the ramp, right? And so it's going to go up this 30-degree rough surface. How do I know it's rough? Well, they told me it has friction. They gave me coefficients, right? And it's going to go up a distance d, and it's going to be a max distance. In other words, it comes to a stop up there, okay? So a split-second stop. Or is it a long time stop? That'll be our question C. But as far as we know, right now, it's just going to come to a stop. What is the acceleration on the ramp? So we know that at the bottom of the ramp, our initial velocity is that same 8 meters per second. And we weren't given that distance, we weren't given time. Should we use kinematics or forces to find the acceleration? If you're like, oh, I love kinematics now. All they gave us are 2 velocities. Is that enough to find acceleration? No. And so let's use forces. Step 1 with forces, do what? Draw a diagram. And so let's draw a diagram when it's on the ramp. It doesn't have acceleration on the horizontal portion, only on the incline. And so here's our object, center of mass. We got gravity straight down. We got normal going. It's perpendicular to the surface, but notice our ramp is kind of reversed from the other ones, right? So don't draw it up and right. It's going to be up and left. Still smaller though than gravity. It's going forward. Let's define our positive direction. It's going forward up the ramp. Friction is going to slow it down by acting down the ramp, okay? And so make sure you still draw it parallel to the surface. And so our surface is tilted. If you want to give yourself some axes for parallel and perpendicular, you can, especially here in the beginning. If that helps, do it. Any other forces? Is there a string, an applied force? Anything else? Nope, that's it. Now, I highly recommend drawing your components of the gravitational force. Remember, if you do it right, Fg is the hypotenuse. And so continue kind of going opposite Fn, draw an equal and opposite Fg perpendicular. So Fn is going to equal Fg perpendicular. And then draw your parallel component that's 90 degrees from that perpendicular component. Squeeze it in there. Bless you. Okay. Now that's not equal to friction. Don't do that. Okay. It's not really equal to anything every single time. But it is down the ramp as well, same as friction. So that'll come into play. Where's our angle? Is it at the top or bottom of that triangle? Hopefully you know that this one's 90. Where is our ramp angle? It's at the top. And if you forget where it goes, old axis, FG. New axis, FG perpendicular. And so it's going to separate those two. And so there's our theta. Okay. And so they want the acceleration. Well, it's going to accelerate in our parallel direction. So step 2, let's write our Fnet parallel statement. And so do we have any forces in the forward direction? We're going up, but no one's really pushing or pulling us up. It's just kind of inertia. Objects going up a ramp, continue going up a ramp until friction and gravity slow it down, right? And so the slowdown, we've got a negative frictional force and a negative, what do I put here? Fg, is that correct? Is Fg parallel to the surface? No, but Fg parallel is. So you have to note that it's a component of gravity, whether you call it Fg parallel or Fgx, or you go straight for mg sine theta, you've got to get the component in there. If you subtract the full weight, wrong. All right, here we go. Cue the vocal cords. F net equals. F net equals. Okay. And so we have MA, and I'm just adding the parallel just to note it's special, equals a negative. What can we plug in for frictional force? Because they did not give me, so many newtons of friction. They only gave us the coefficients of friction. And so what's our new equation for frictional force using coefficient? Mu times, it's on the formula chart, Fn, right. And so mu Fn. Now, which mu am I going to go grab? The static or the kinetic? Kinetic. When you're accelerating, technically you're moving, right? Probably. And so I'm going to use the kinetic version of everything. And so mu Fn. Well, hold up. Fn, does it equal the weight? Not on a ramp. Fn equals FGY, or FG perpendicular. Well, if you look at the triangle, what trig function can I plug in for FG perpendicular? MG. If you look at the triangle, the perpendicular component is adjacent to the ramp angle. FG is always your hypotenuse, so it would be the weight times cosine theta. So that long expression, notice I'm not plugging numbers in yet. Okay, that long expression is the frictional force. I can carry it down to my F net statement. And so minus mu mg cosine theta. And then we have FG parallel. Well, FG parallel, if you look at the triangle, is opposite. FG is your hypotenuse, so which trig function are we going to use for the parallel component? Mg sine theta. Look at that expression. Aren't you glad we started out with a frictionless ramp? Okay. Ramps with friction, I don't want to say it's the hardest thing you'll see, but it definitely ramps it up. Okay, thank you. Okay, what are we doing all this for? We're trying to solve for the acceleration. Oh, did they give me the mass? Uh-oh, they did not give me the mass. All is lost. I can't do this, or can we? When you put it in variable form, every single term, MA, mg cosine theta, mg sine theta. What happens if you divide the whole thing by mass? Boom, boom, boom. We get acceleration is equal to a minus. If you go back up and see mu k, they told us was 0.4 times gravity times cosine, I think it stayed 30, minus 10 sine 30. And so a concept while you punch it in, notice your acceleration up this ramp depends on your coefficient of friction. So friction plays a role, gravity plays a role, and as we saw earlier, the angle of the ramp plays a role. That's it. Your mass, acceleration is independent of your mass. Okay, so sine 30 is 1/2 times 10. So I know the last number is going to be 5. What is 4 cosine 30? Does anyone have that one? 3.4 cosine 30? What did you calculate it? 3.5. Okay. So 3.5 minus 5. What's our acceleration? Negative 8.5 meters per second squared. Negative, just meaning as you go up the ramp, you're accelerating down the ramp, right? And that's pretty close to gravity. That's actually a pretty strong acceleration for an object, FYI. Okay. Good on acceleration. Ramps with friction. B should go quick. B says, now that you know the acceleration, how far will it slide up the incline? So we know two velocities, we know the acceleration. We're trying to find that labeled distance, right? Or delta x, either way. And so initial 8 meters per second, final comes to a stop. Now, whether it's a permanent stop or a temporary stop, that's part C. And we know the acceleration is negative 8.5. What equation are we going to use to find D? Third one. And so VF squared equals VI squared plus 2A delta X. So I'm running out of room there. 8 squared is 64. I got to subtract it to the other side technically. And so if you have negative on the left, negative on the right, going to cancel out. But 64 divided by the product of 2 times 8.5 is going to be what? A delta X equal to a positive. When you get an answer, let me know. Okay, 3.76, and it's a distance, it should be in meters. Okay, so far it's been moving, it's been kinetic. The box comes to a stop. C is basically saying, what's going to happen at the top? What it's really saying is it going to be a permanent stop or just a temporary stop? For it to be a permanent stop, so let me add that, permanent, or is it temporary? Temporary stop. And so how are we going to figure this out? If it's a permanent stop, what's going to be true? That kinetic friction goes away. Stopped objects, stationary objects, have what kind of friction? Static. Have we done anything with point A? Have we done anything with static friction? No. And if you remember, here's your little review from last time. Okay, our friction graph, you saw it experimentally, how it comes to be. This is a simplified version. So static, you can be several different levels of static friction, but when you calculate with the coefficient, it's a maximum static. And so force of friction, static max, is the one that's equal to mu S times Fn. I can't calculate the other levels unless I'm doing Newton's first law, right? Friction's just going to balance whatever gravitational force trying to pull it down. And so we're going to calculate the maximum, and then we're going to compare it, okay? And so let's assume for a second it comes to a stop, permanent stop. And so what would our diagram look like? Let's see. And so if it's at a stop, what forces are working on it? We got that gravitational force and the normal force, same. But if it stops, friction, static friction, still down the ramp? Who's pulling it down the ramp? Put a box on a ramp, if it goes down, who's responsible? Gravity. So maybe we draw in our components. Parallel, perpendicular. And so there's a parallel component of gravity pulling it down. But if it comes to a permanent stop, friction, static friction, is going to be directed what direction? Up the ramp. And so maybe if it's static friction, it's holding it up. Because those two, the parallel component of gravity trying to pull it down, and then the static gripping friction trying to hold it in place, I got to compare these two. Okay, so what we're going to do is calculate the maximum static friction. That's our limit. Maybe we're at the limit, maybe we're not. So we got to compare that FFS max to the FG parallel, bringing it down. Okay. Everybody good with our game plan? So let's calculate that maximum static friction. And so FFS max equals mu s, but instead of Fn, we're on a ramp. Fn equals what? If you look at your diagram, Fn is going to balance FG perpendicular, okay? And so FG perpendicular, I can plug in for Fn, and FG perpendicular is adjacent to my angle, if you put the angle at the top. And again, that's not random, that's geometry. And so what would be our substituted equation for FG perpendicular? Mg cosine theta. So mu s mg cosine theta. Now make sure you get the right coefficient. Mu s is bigger than mu k. And if you scroll back up, I think they told us it was 0.8. Now let me warn you, your coefficients are not always a 1-to-2 ratio, okay? Don't memorize anything like that. But static is greater than kinetic. Again, it's harder to move a stationary object than it is an object already in motion. We talked about pushing a stalled car maybe last time? Yes? Okay. And so mu s is 0.8. Now mass is not going to cancel right here. Did they give me the mass? Not yet. And so I'm just going to keep it as an m for now. I haven't plugged it into anything else. But g, I know, is 10 times cosine, the angle was 30. And so keep the m. It won't be meters, but it'll be the variable m. 0.8 times 10 is 8 times cosine 30. We get what? 6.9. Okay, so 6.9 mass is our maximum static friction. Now that's not an answer. That's what we're going to use to compare FG parallel to. FG parallel should go quicker. That's the opposite component in our triangle. And so we'll use mg times sine theta. Again, we don't know mass, so just keep it as an m. And so 10 times sine 30 times m, right? So sine 30 is 1/2 times 10 is 5. We'd have 5m for FG parallel, okay? And so we got to compare these two. FG parallel, the amount pulling it down is 5m. If you make mass 1, maybe it's a little easier, but we've got a component of gravity pulling it down by a factor of 5. Our maximum, it's going to stay at rest until it reaches 6.9. So is it a permanent stop? Or is friction not enough? Is static friction not enough and it slides back down? So FG parallel is less than the static max. And so if we compare that to our graph, maybe 6.9m is at the max, but maybe 5m is here. Now, don't start thinking, oh, it could be kinetic. That uses a different coefficient. You'd have to calculate that separate, right? But it did come to a stop, and it looks like we have enough, right? 5m, if gravity pulls it down at 5m, well, friction's only going to react with 5m up. We have not reached the maximum. And so it will be a complete stop. And it'll just stay there. So what happens at the top? It stops and it stays at a stop. Good deal? When would it move? What would it be? Well, if gravity was pulling down more than static maximum friction or gripping, maybe your static friction came out 4.9. Gravity pulls it down 5. Friction can only hold it stationary until 4.9. And so if gravity was bigger, then gravity would win and it would slide down. Does that comparison make sense? Okay. All right, next time we will continue doing friction. We will continue doing ramps, but we're going to throw one more piece into the mix, pulleys. And so what happens when I have a system of objects with a pulley? All right. Okay. If you got questions, let me know. Otherwise, plug your laptop in and have a good day.